The next topic is parametric curves, and if you're following along in the Thomas textbook, this corresponds to sections 11.1 and 11.2, which we'll do together. So first, just to set the topic, let's suppose that we have a curve given by a function. We have y as a function of x, or I've written here y equals f of x. Then, as we've talked about before, every point on the curve has the form x comma f of x. The thing is that this form only works if you can actually write y as a function of x, and as many of you know, that means, of course, that the function has to pass, let's say, the vertical line test. It has to there has to be only a single y value for every x value. However, there are lots of curves that don't meet this condition. Just for example, a circle we know is certainly a perfectly valid curve, but can't be written as a single function. So what we want to do is define the notion of a parametric curve. What we do is we define something called a parameter, which we usually call t, where t is just an independent variable, and you'll see in a minute how we use that. So then what we're going to do is we're going to define two functions, x of t and y of t. So these are both functions of the variable t. And then we'll say that each point on the curve is given by x of t comma y of t. So instead of saying that at one of the parts of the point, the x part, is independent and then the y part is a function of x, instead we just say that both the x and the y parts are functions of some other variable called t that we don't even graph. So usually, one of the notations that's fairly common is to define the parameterized curve or path. Frequently, we're talking about motion along this curve, which is why I would call it a path, where we define that as c of t is equal to, and then this expression giving x of t comma y of t in parentheses, representing each point on the curve. You often see the variables r of t or s of t used in this place. I often just call it c of t for a curve. So let's just to give an example of what a curve would look like if defined in this way and how you would define such a curve. Let's suppose that x of t is equal to t cubed minus 1 and y of t is equal to t squared minus 2. So let's sketch the curve c of t equals x of t comma y of t. Now, we're making certain assumptions here. We're going to assume that t is defined for all real numbers. That's not always going to be the case. But by default, if we don't say what the domain of t is, we'll assume that it's just all the real numbers. So what we want to do, there are a couple of ways you can do this, but perhaps the simplest way to start is just by plotting a couple of points. So let's put up a chart here. What we want to do is choose t, x, and y. And of course, x and y are just going to be functions of t, which are defined here. I'm just writing them as x and y because that's how we're going to use them. Now we can pick basically any values of t because t is an independent variable. It's x and y that are going to be functions of t. So I'm just going to pick fairly convenient values of x and y that are close to 0 because they're easy to work with. So I'm going to choose 0, 1, 2, -1, and -2. All right, so we can fill in x. Let's do x and y for t equals 0. When I plug in t equals 0 into the equation for x, I get 0 cubed minus 1, which is -1. And when I plug 0 into the equation for into the function for y, I get 0 squared minus 2, which is -2. So I'm just going to zip through filling in a couple of other values, which you can imagine plugging in these values of t into the equations for x and y. Okay, so now we have several values of x and y, and we can simply plot the curve. So let's put up a graph, and let's put in some numbers. Let's just go 5, 10, -5, and -10 like that, and 2, 3. Okay, so I've just put in a little bit of scale. Obviously, these are not the same scale for the x and y. I just want to be able to graph this. So the first one, you go there. It has the point -1, -2, so that's going to be roughly here. Actually, let me do this in a different color. Then we have the point 0, -1, so that's going to be there. And then 7, 2, so that's going to be roughly there. And then -2, -1 will be roughly there, and -9, 2 will be about there. So filling this in, we can see The curve looks something like that. So there's our curve defined parametrically. And by the way, just take note of where the actual points are here. So this is generated by t. So that's t equals 0. Over here, we have t equals 1. This is t equals 2. This is going to be t equals negative 1. And this is going to be t equals negative 2. You see, I didn't even graph t because that's not one of the variables that we're graphing. It's just the parameter that we're using to generate these points. One interpretation of what we're doing, and it explains why we're calling this variable t, is that you can think of this as though t is the time variable, as t is the thing that simply moves for either forward, or we can talk about times in the past. So what we can say is that at some arbitrary time 0, the object was right here. And then at time 1 it moved here, and at time 2 it was here. And perhaps t equals 0 was arbitrary. Maybe the object came from someplace, and 1 second ago it was over here, and 2 seconds ago it was over here. So you can think of this almost as a path of an object moving through space as time proceeds forward. That's one interpretation of the parameter. And if you go on in physics or any form of mechanical engineering, you will frequently see motion described in this way.